Hello, Algebra Tours. Today we're going to be talking about something you've never seen before, and that is called imaginary and complex numbers. That is right. We are going to be talking about numbers that are imaginary, not real, imaginary and complex. So what you are going to need today are your notes, a pen or a pencil, and a calculator. So once upon a time, a man or a woman sat down to solve a quadratic equation. And how they are to solve this quadratic equation is they would think to themselves in their mathematical mind, oh, well, this is simple. All I need to do is get the x squared alone. So in order to do that, I need to subtract 10 from both sides, canceling this, leaving me with x squared on the left and a negative 10 on the right. Oh, well, if I need to get rid of the squared on the x, I'm going to take the square root. And this is where it falls apart. If we were to plug into our calculator a square root of a negative 10, this man who sat down to solve this equation would have no solution or an error message from their calculator. So this man did not like what he sees, and he knows if I have a quadratic equation or I have an x squared term, that tells me that I need to have two solutions. How in the heck is the calculator telling me that I have no solutions? What is going on? So this man is named Descartes. He was a French man who discovered that sometimes this can happen where the fundamental theorem of algebra breaks down, or if we say since it's x squared plus something equal to something or whatever, we need to have two solutions, right? The greatest exponent in any equation tells me how many solutions I have to have. And he was the one that discovered not all the time could you actually find a solution. And that breaks apart the whole theorem of algebra and everything algebra stands for. So since Descartes broke through on this mathematical discovery in the 1600s, he decided, you guys, he decided to invent a new number system, new types of numbers in the 1600s. This man was so smart and he was so genius. Maybe you've heard about Descartes, maybe you'll keep hearing about him if you continue on in the math world, but he decided to invent a new number system called imaginary numbers, and that is where they are born, and that is what we will be talking about today. So Descartes set up the imaginary number system so that you would call the number I, and the value that I would be equal to is the square root of negative 1. So in your notes, you should probably write down under imaginary numbers that I, which is a number, is equal to the square root of negative 1. So rather than writing the square root of negative 1 everywhere and trying to figure out what that value is equal to, he assigned a letter or a letter to represent the number, which is I. So he decided if I'm going to let I equal the square root of negative 1, then I squared would have to be negative 1. So if you squared both sides on this, whenever you square a square root, that cancels it out. And whatever you do to one side of an equation, you have to do to the other. So what he's saying is if I equals the square root of negative 1, then it must be so that I squared has to equal negative 1. This, ladies and gentlemen, is the biggest takeaway for today. These two things, I is equal to the square root of negative 1 and I squared is equal to negative 1. So make sure that you have these two things written down in your notes. Okay, so now that we know how Descartes assigned the i's, I and I squared, and what it means, let's start doing some problems with them. So we have these three problems, and up until this point in your mathematical careers, you thought these things had no solution. If you punched into your calculator the square root of a negative 25, you got back error, and your teachers previous to me said, oh, that means no solution, don't worry about it. Now we're going to have to etch a sketch that part of our brain or erase that part of our brain because we can keep simplifying these square roots down and we can keep solving, okay? So we're going to break down every single one of these into the I part and the real part, okay? So the square root of negative 25 can be broken down into negative 1 times the square root of negative 20, or the square root of 25. So you can break whatever is underneath this radical sign, you can break up into multiple parts or multiple factors as long as it's still existing underneath the square root, okay? So we know now that the square root of negative 1 is I, and the square root of 25 is 5. So my solution, or my answer now, is 5i. The proper way to write these is the whole number first and then the I. Okay, so now let's break down the square root of negative 6. So we can break this into the square root of negative 1 times the square root of 6. We know the square root of negative 1 is I. Thank you, Descartes. The square root of 6 cannot be broken down because 6 is not a perfect square, and 6 doesn't have any factors that are perfect squares, so that's going to stay as it is. So how we write these is we put the I first and then the square root. So the proper way to write all of these solutions is a whole number and then the I and then the square root. That's the order in which you should write them. If you write the square root of 6 times I, that's okay. I'll understand what you mean, but we should get in the habit of writing it this way. Okay, and now the last example is the square root of negative 40. So we can break this into the square root of negative 1 times the square root of 40. We know that the square root of negative 1 is I, and we know that 40 can be broken down further into more square roots because 40 has a perfect square of 4 as a factor and 10. So we can break down 40 into 4 times 10 underneath the radical, and we know even further that the square root of 4 is 2. So my final answer for this one is going to be 2i times the square root of 10. So this is the proper way in which we write, or how Descartes wanted us to write answers, in this way. Let's try 2 more examples. So now we have 5 times the square root of negative 48. So let's break that negative 48 into the square root of negative 1 and the square root of 48. We aren't getting rid of the 5, so I'm just going to bring him down on each step because he's still part of my problem, okay? So we know that the square root of negative 1 is I, and we bring the 5 down. Now we need to break up the square root of 48 because we know that 48 can be broken down. One of the factors of 48 is 16, which is also a perfect square, times the square root of 3, because 16 times 3 gets me back to 48. Okay, so we have 5i times the square root of 16 is 4 times the square root of 3. Well, since the 5i and 4 are all out in front of the square root of 3, those are all getting multiplied, okay? It's 5 times I times 4 times the square root of 3. So we can simplify 5 times 4, which we know to be 20. I stays I, and the square root of 3 stays the square root of 3. So my final answer is 20i square roots of 3. Now I have the square root of negative 10 over 3. Well, we know back from Algebra 1, properties of radicals say that if we have a fraction underneath a radical sign, we can break it up into the square root of 10 over the square root of 3. We can do that, okay? And then we can break up the square root of negative 10 into the square root of negative 1 times the square root of 10 all over the square root of 3. We know that the square root of negative 1 is I, square roots of 10 all over the square root of 3. And hopefully you've seen this before, but when we have a fraction and our denominator is a square root, that is improper. So in order to simplify fully, I have to multiply the top by the square root of 3 and the bottom by the square root of 3. And we call that rationalizing the denominator. Hopefully you're familiar with that. If you're not, this is what you have to do. Whenever you see a radical in the denominator, you have to multiply the top and the bottom by that same radical, or the square root of 3 in this case. So when we multiply across the top, we're saying I times the square root of 10 times the square root of 3. We know that if 10 and 3 are both underneath the radical, we can simplify that into just one square root of 30. Okay? And then in the bottom, we have the square root of 3 times the square root of 3. So we can multiply the 3 times the 3, so we get the square root of 9. And we know that the square root of 9 is 3. So my final answer is I square roots of 30 all over 3. So what we haven't talked about yet is the complex numbers. And complex numbers are numbers that have a real part and an imaginary part. Okay, so now we're going to ask ourselves, how do I operate or simplify with complex numbers, or numbers that have a part that is real and a part that's imaginary? So we're going to look at 3 examples. This first example is saying I times 3 plus I. So just like you would, in Algebra 1 and what we've done in the past, you would distribute the I. So I times 3 is simply 3I. I times I is I squared. If you remember from one of the first slides and notes that we took today, we said I squared is the same thing as -1. So we can replace this I squared with a -1. So we would have 3I minus 1. For complex numbers though, you need to have the real part come first and the imaginary part come second. You have to have that, okay? So it would be improper or wrong if we wrote this answer as 3I minus 1. The correct answer would be -1, so you want to bring him out front and you want to put the imaginary 1 in the back, plus 3I. So my final answer is -1 plus 3I. Now we have an addition happening. So we have a complex number. We have 3 plus 2I. The real part's 3. The imaginary part is 2I because it has the I in it, plus another complex number, 4 minus 6I. So just as you would imagine, we have to add the real parts together, so 3 plus 4, and we have to add the imaginary parts together, which is 2I plus a -6I, or minus 6I. So 3 plus 4 is 7, 2I minus 6I is minus 4I. We already have our real part first and our imaginary part second, so my final answer would be 7 minus 4I. And now we have one more example that we're going to do together. And this is 2 complex numbers getting multiplied together. So we're saying 3I times 6, or plus 6 times 4 minus 5I. So we would have to FOIL. So we need to take 3I times 4, which is 12I. We have to take 3I times 5I, which is going to be minus 15I squared, because my 5 was negative. And now we need to take 6 times 4, which is a plus 24. 6 times a -5I, which is minus 30I. And now from here we have to simplify. Well, you'll notice again that we have this I squared, which is a -1. So we can replace him with a -1, and that's getting multiplied by this -15. So we're going to have 12I plus 15, because we're taking -15 times -1, plus 24, minus 30I. And now we need the real part to come first and the imaginary part to come second. So let's do the real numbers, which is 15 plus 24, which is 39. And now we have to do the imaginary part, which is 12I minus 30I, which is going to be a -18I. And that, ladies and gentlemen, is my final answer, 39 minus 18I. So biggest takeaways today are that I is equal to the square root of 1, I squared is equal to -1, and complex numbers have a real part and an imaginary part, where the real part comes first and the imaginary part comes second. So thank you so much for taking good notes, and I shall see you soon.